Alright, welcome to Math 150, Section 2, Lecture 16. What we're going to do today is we're going to do the theory of multivariable integration at warp speed, because it's essentially the theory of one-dimensional integration, with some key differences. And the key differences we're going to spend a lot of time over the next week or two. And the key differences are switching orders of integration, which you really can't do when you have a one-dimensional problem because there's only one integral. And then the big one is change of variables. Change of variables is essentially use substitution. So what are the big three coordinate transformations we've learned so far this semester? Cylindrical, polar, and spherical. So we're going to do a lot with those and justify how things change. Okay? There's really 4 units to the course. The first is all that your wonderful material in chapter 11 on lines and tangent planes and dot products and vectors. It's the notation. Then there's chapter 12, which is differentiation, which is basically everything that's before. Just if you want to take the partial with respect to x, hold y constant. Then there's a couple of tricks. Well, when can I interchange the order of differentiation? When is a function of several variables differentiable? But it's essentially one variable calculus. Now we're in the unit on integration. One of the things you learn, sadly, is that integration is hard. It is very difficult to find an antiderivative in general. We work hard to give you good problems. And so we'll learn integration techniques. And then the last part of the course is sequences in series. And I will do a little bit of that today. I'm trying to throw some of this material in throughout so that you see it multiple times. So how many of you have ever seen this function, natural log of x? Good. I mean, we've done it in this class, so I'm basically asking who's awake right now. What's the derivative of natural log of x? 1 over x. Excellent. What's its antiderivative? Wonderful. Remember to email me. So how many of you have seen that the antiderivative is x log x minus x? So one way to get this answer is the method of divine inspiration. It's a wonderful method for those of you who are concerned about the midterm. You won't learn it. The problem, of course, with divine inspiration is you don't know when it's going to hit. But if I give you this, how could you check and see if I'm right? Take the derivative. So there are a lot of things in life which are hard to find, but easy to verify. My daughter had a homework problem where she had a bunch of numbers with plus minus times divided, in fixed locations between them, and you had to put in a parentheses so that the result was equal to the number on the far right. It took her a little bit of time to get some of them. Does it take me much time to check and see if she's right? No, once the parentheses are, it's not because I have a math PhD. Once you have the parentheses in, it's very easy to go through and check and see, does this equal the answer that they give you on the right? And when you look at all the different possibilities, it's much harder. One of the ways to get this is the method of divine inspiration, or guessing, and then adjusting your guess. And this is actually very useful if you continue to differential equations. Let's guess that the antiderivative is x log x. And this is not a bad guess, because when I use the product rule to find the derivative, I get the derivative of x times natural log of x plus x times the derivative of the natural log of x. And the reason I'm doing this is the derivative of x is 1. So this starts off with the natural log of x, which is exactly what I want. But then I have plus x times 1 over x, so I get the natural log of x plus 1. So the answer is wrong, but it's wrong in a very good way. My derivative is too much by 1. So I want to subtract something that has a derivative of 1. And that's where the minus x comes from. As a nice exercise, be divinely inspired and find the antiderivatives of either the natural log of x squared or the natural log of x to the nth power. Do nice formulas for these exist? Sometimes yes, sometimes no. So sometimes problems that look hard at first, it turns out there is a nice solution to them. This is the first lecture that I think is going to be fundamentally different, at least in potentially, from section 1. Because a lot of this is just going to be based on your responses, which way we go on a lot of these problems. All right, so the challenge when you need to do integration is that it's very hard to get closed form solutions for the antiderivatives. So we have the theory. What's the nicest region you can think of for two variables? What region would you love to integrate over? A rectangle, right? If you had a choice, you would want a rectangle. And then we can do it exactly as before. Let's chop it up into thirds. Or we could chop it up into sixths. And then we can just play the game exactly as we did in one dimension. And you get your upper sums, you get your lower sums, you show that the upper and the lower sums converge to a common value, and you call that the integral. And this would essentially be giving us the volume under a surface. Most regions are not rectangles. So what you would want to do is you want to like a rectangular approximation. So if I gave you something like this, what you would do is you would start choosing a bunch of points on the boundary. You just kind of like walk in a rectangular manner around it. And the idea is if you choose enough points and your boundary is sufficiently nice, the error should become smaller and smaller and smaller and smaller. So let's say that we're never missing by more than epsilon. Then the hope is that since it's got a finite perimeter, the most we'd be missing is epsilon times the length of the perimeter times the maximum value of the function in absolute value. And that because epsilon is sufficiently small, we could make this work. And we'll just expand things out. So that's essentially the theory. And in an upper level course with real analysis, we'll make this more rigorous. All right. Notationally, if I write x goes from a to b, integral y goes from c to d, f of x, y, dy, dx, this means I start at the point AC, I end at the point BD. And it's very similar to the partial derivatives. When you wrote f sub x, y, it's first the derivative with respect to x, then the derivative with respect to y. You start inside and you work your way outside. Over here, it's the same thing. I start inside. I first integrate with respect to y, and then I integrate with respect to x. Do I have to write y and x down here? Can I just write c to d and a to b?
No. It makes it confusing.
It makes it confusing, but am I allowed to confuse you? I'm a professor. I have incredible freedom in my class. Most textbooks do not write x and y. If you write dy and dx, you don't need to. It's clear from that what's going on. Well, it may be clear, but it's, I think, clearer if you write it like this and you can glance down and you can see. And so again, I think it's worth taking a little bit of extra time, especially if you're going to be doing changes of variables, to just always write down x goes from, y goes from, to really remind you what's moving. So what we're doing here is I first fix a value of x. And then once I fix the value of x, y goes from c to d. And then I vary x. So I'm first integrating vertically, then I integrate horizontally. You could, of course, for this problem, do it the other way around. You could first fix the value of y and do a horizontal integral, and then go up and down. The hope is that this should be the same as integral y goes from c to d, integral x goes from a to b, f of x, y, dx, dy. So someone tell me why that should be, why they should be equal. Why is this a reasonable thing to hope for?
You're multiplying them out together, so what's the rule if you multiply two things together?
Yeah, so multiplication is commutative.
Yeah.
But basically, if I'm dividing this up into boxes, if I first count the boxes vertically and then go horizontally, that should really be the same as counting horizontally and then counting vertically. Unfortunately, this is not always the case. But if you think back to partial derivatives, it was not always the case that you could interchange orders of differentiation. So there are two things that go on that we need in order for things to be nice. So when we did the proof in one variable of the fundamental theorem of calculus, we assumed something about the region, and we assumed something about the function. What do we assume about the function? It's continuous. And what do we assume about the region? What do we assume about the region?
It's bounded.
It's bounded. The region was finite. Whenever there is an infinite in mathematics, you have to be careful. So rather than proving in general why these two are the same, I thought I would prove to you why they might be different. And just warn you as to what's going on and give you, here's the key theorem that you have to be aware of. So it's going to be Fubini's theorem about when you can switch the orders. All right. Maybe before class I will play a clip from my son on how to switch orders from when he was about 2 years old. I'm going to give you an example, but to make my life easy, I'm going to give an example involving a double sum. Okay? I could convert the double sum to an integral by just smearing things out. It's just going to be a lot easier to write it as a sum. So here is compare the sum n goes from 0 to infinity, the sum n goes from 0 to infinity of a and n to the sum n goes from 0 to infinity, sum m goes from 0 to infinity of a and n. And I'm going to define it as follows. So fortunately we have a lot of experience drawing dots from last class. So draw a bunch of dots. And these dots will go off to infinity. And I'm going to define my sequence as follows. It's plus 1 here, this is the point 0, 0, minus 1 here, and then 0 for the rest of eternity going on. This point over here is 0, 1. It's going to be 0, plus 1, minus 1, and then 0 for all eternity. This is the point, this is the point 1, 0, sorry. This is the point 2, 0. It's going to be 0, 0, plus 1, minus 1, 0 for all eternity. Next one is going to be 3, 0. It's going to be 0, 0, 0, plus 1, minus 1, 0 for all eternity. So let's do vertical first, then horizontal. So if I look at any vertical column, what is the sum in any vertical column? 0. Every vertical column, plus 1, minus 1, they cancel. Plus 1, minus 1, they cancel. Every vertical column is 0. So if I do the vertical sum first, followed by the horizontal sum, what do I get? 0. What if I do horizontal, then vertical? What's the sum of in the third row? Fourth row, fifth row, second row, first row? 1. So if you do horizontal then vertical, you get 1. If you do vertical then horizontal, you get 0. This shows that the order of integration matters. What's going on here? Well, we have an infinite region, and that's what causes problems. So what I'm going to do is I'm going to state the Fubini theorem, and we'll talk just a little bit more about the dangers of infinities. And this is why we're so careful. This is why you have so much of an emphasis in Calc 1 on proper integrals. I think that's the phrase they use. Integrals from A to B, you're not allowing infinity. And I think they use indefinite integral or improper integrals, yes?
Isn't still 0? The first column you have negative 1, and then the last column you have...
No, because this goes off to infinity. So the next one is going to be 0, 0, 0, 0, plus 1, minus 1.
Okay.
So it goes off to infinity. If it was in a finite region, it would be 0, they would be the same. But because it's an infinite region, we have trouble. So the big result is Fubini's theorem. So if f is continuous on a closed, bounded, nice set, then you can interchange integrals. What's really going on here, what's lurking in the background, is a nice result from real analysis. And the real analysis result is that if you have a continuous function on a nice bounded set, then it attains its maximum, it attains its minimum. In particular, it's bounded. So the real result is, more generally, you can interchange if the integral of the absolute value of f of xy dx dy is finite. So if you put in an absolute value and integrate, or dy dx, any of those integrals being finite, then you can interchange. The danger is when you have an infinity. So, again, rather than proving the general theorem, I want to just give you an example of how you have to be careful. So later in the semester, we are going to do a lot on sequences and series. And so whenever possible, I want to try to give some examples early in the course as just you're building up some notation. So let's look at the harmonic series. 1 plus a half, plus a third, plus a fourth, plus a fifth, plus a sixth, plus a seventh, plus an eighth, plus a ninth. I'm getting tired. I hope the pattern is clear. Okay. How many of you have seen the harmonic series before? Okay. How many of you know that the harmonic series that this sum goes off to infinity? Okay. How many of you can prove that? Does anybody remember how you prove this in a calculus class that this sum diverges? Does anybody remember the integral test? Okay, so we will be doing the integral test later in the semester. I'm going to give you a really quick, easy proof that the harmonic series diverges. Does everyone agree that 1/2 is greater than or equal to 1/2? Okay. 1/3 plus 1/4 is greater than or equal to what? A lot of things, but there's one really good thing. It's greater than or equal to what?
1/3.
I'm sorry?
1/3.
It's greater than 1/3, but I want something a little bit larger than a third. Sorry, greater than a fourth. I want something larger than, well, 1/4 is less than 1/3, so I want something larger than a third. If I go, yes, it's greater than or equal to 1/2. If I replace the 1/3 with 1/4, I get 2/4. If I sum 1/5 plus 1/6 plus 1/7 plus 1/8, that will be greater than or equal to what? 4/8 or 1/2. What this shows you, if I then go from 1/9 all the way up to 1/16, that sum will be at least 1/2. If I go from 1/17 to 1/32, that sum will be at least 1/2. This sum diverges. So the harmonic sum diverges. And in fact, we can even use this to get a sense of how rapidly it diverges. I want to show you now how you have to be extremely careful with infinities. Does anybody have a favorite number that they don't mind sharing?
15.
15, okay. Let's look at 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, plus a seventh, minus an eighth, plus a ninth, minus a blah. Okay? You said your favorite number is 15. So what I'm going to do is I'm going to rearrange the sum so that it converges to 15 when I rearrange the terms. Okay? If I look at the sum of just the positive terms, that goes to infinity. If I look at the sum of just the negative terms, that goes to infinity. So what I do is I take the positive terms starting at 1, and I add a third, a fifth, a seventh, a ninth, and I keep adding them until I first break 15. Then I take the negative terms, starting with negative a half, and I keep subtracting them until I just get below 15. Then I add positive terms again until I just break 15. Then I take negative terms until I get just below 15, and I keep alternating. And because the terms are getting smaller and smaller and smaller, the amount I overshoot 15 above or undershoot below is going to get smaller and smaller and smaller. And so in the limit, I can rearrange these terms so that the sum equals 15. There's nothing special mathematically about 15 for this problem. There might be special things about 15 for other problems. You can do this with any number. This is called the rearrangement theorem. I can make this sum by rearranging the terms equal anything I want. The point of this is to show you why we need pure math, why we need things like the Fubini theorem. That when you have infinities, strange shit can happen. Okay? I'll edit that out later. So the last thing to note is if you replace this, plus 1 minus 1 plus 1 minus 1, if you use a coin and say maybe with probability 1/2 I get a plus sign, probability 1/2 I get a minus sign, it turns out we can say an awful lot about sequences like that. So there's a lot of nice things that can come from something like this. Okay. So what I want to do now is I want to talk a little bit about finding areas, finding volumes, doing some applications of what we're doing. A lot of this is to prepare for getting to the change of variable formula, to convert from, say, Cartesian coordinates to polar or spherical. This is a first lecture So I am not going to prove or justify the change of variable formula. I'm going to just state it at one point, and we're going to just see some consequences as motivation as to why we should then spend so much time caring about this theory later. We're going to see how powerful it is. So we will start off with a circle. X squared plus y squared is less than or equal to 1. This is the coordinate. This is the equation of the circle in Cartesian coordinates. What does the circle look like in polar coordinates? Box. So here's theta, here's r. So what would be the equation of a circle in polar coordinates? Good. R less than or equal to 1, and this is polar. What's the area of a circle? Pi r squared. And so here, let's do radius r, big R. So we'll do pi big R squared. What's the area of this box? This is big R here. This is 2 pi here. So what's the area? 2 pi times the radius. This should seem wrong. They're the same object, right? I've just written them down differently, but they don't have the same area. The problem is the conversion factor. Now, you're often used to nice conversions. If I want to convert dollars to euros, if I know how much euros I get with $1, if I had $2, I would get twice as much. If I had 4, I would have 4 times as much. Here, an area element does not always convert to the same thing. And so what happens is the area element dx dy gets converted to r dr d theta. And we will prove why this is true later. So the conversion factor depends on where you are. Let's think about whether or not this makes sense. Imagine x and y are in meters. Then your area is going to be meters squared. Makes sense. If x and y are in meters, what units will r have? Meters. Theta is unitless. If I just gave you a dr d theta, that would have units of length. I want an area. So dr d theta can't be the correct conversion factor. You really should not write this as r dr d theta. How should you write this? I want to have 2 lengths. dr is already a length. I should write this really as dr times r d theta. The r d theta is actually going to be a length. And now this will have the proper unit. So what we're going to do for the rest of the class is we're going to do some integration examples. So let's start off by trying to calculate the area of a circle. Area of a circle. I claim it's enough to do a quarter circle and multiply by 4. Okay? And what I will do is I will start off with the quarter circle, and I'll do a circle of radius 1. We can, of course, adjust this to a more general radius, but let's start off with a circle of radius 1. So this top curve is x squared plus y squared equals 1. So if I want to solve for y in terms of x, I would get y is the square root of 1 minus x squared. It's really, of course, plus or minus. The minus would be the one down below. And so this gets into the vertically simple and the horizontally simple regions in the book. If I want to do vertically simple, I need my bottom curve, my y1 of x, and my top curve, y2 of x. I fix an x, and I go up like this. So for this problem, I would have 4, x goes from 0 to 1, y goes from y1 of x to y2 of x, and you just integrate the function 1 dy dx. So we have to figure out what is y1 of x. So what would y1 of x be for this problem? What's the lower boundary curve? 0. So for this problem, y1 of x is 0, y2 of x is the square root of 1 minus x squared. And so we get that the area is 4, integral x goes from 0 to 1, integral y goes from 0 to the square root of 1 minus x squared, 1 dy dx. Right, so we have two integrals to do. I'll do the first and I'll leave the second for you. So the first one, we get 4, integral x goes from 0 to 1. Right, what's the antiderivative of 1 with respect to y? It's just y. I evaluate at the top and I subtract the bottom. So I get the square root of 1 minus x squared dx. And I'll just leave that for you guys. What function has derivative square root of 1 minus x squared? So this is the glories of going online. I went to Wolfram Alpha. I typed integrate square root of 1 minus x squared with respect to x. And it's 1/2 quantity square root of 1 minus x squared times x plus the arc sine of x. What could you do if you believe that that's the answer? I'm sorry? Find the derivative. Check it, right? This is the method of divine inspiration. If you have a candidate, you can check. How would you get a candidate like that? Well, you might remember the derivative of arctangent was 1 over 1 plus x squared. So maybe let's look at the derivatives of maybe arcsine, or maybe arccosine, and see what goes on. You could also, of course, try to do trig substitution here. I'm going to try to avoid that right now. The point is to show you how bad this integral is, and that you don't want to do this integral. And that if you have a circle, you should not be integrating in Cartesian coordinates. You should be using polar coordinates. It is to be deliberately painful here to drive home the point that you don't want to do this. All right? Let's look at arcsine of x. Well, if we take the sine of the arcsine, what will that equal? X. So by our rule from before, we get arcsine prime of x is 1 over sine prime at arcsine of x. All right, that's 1 over cosine of arcsine of x. Now we just have to figure out what is the cosine of arcsine. So I draw my triangle. Here's my angle theta. Let's let theta be arcsine of x. So I need to draw a right triangle whose angle theta has a sine of x. Well, if I make the hypotenuse 1 and this x, the sine of that is going to just be x. The cosine, well, what would the bottom length be? What's the length of the base? Square root of 1 minus x squared. So this is just by Pythagoras. So we would then get 1 over the square root of 1 minus x squared. So the derivative of arcsine is 1 over the square root of 1 minus x squared. So what you might do from this is say, okay, well, maybe if I start off with the square root of 1 minus x squared and take a derivative of that, then I'll get a 1 over square root of 1 minus x squared, and maybe the arcsine will come in, and maybe I can then somehow get an expression for the antiderivative of this. So I will leave this as a painful exercise for you. Yeah. It's not bad to try this, just to get a sense of how bad this calculation is. But if we could find the antiderivative, we'd be done, we would have the area of the circle. What I want to do now is I want to calculate the area of the circle in polar coordinates. And what I will do is I will assume that we have the correct change of variable formula, that the element dx dy goes to r dr d theta. That is something we're going to have to prove, but this is trying to motivate when we get to that. All right, so we will erase all of this. This is painful. We don't want to do this. And we will try to do this using polar coordinates. So, area of the circle. So we would have 4 integral r goes from 0 to 1, integral theta goes from 0 to pi halves. Because remember, we're doing a quarter circle. So the radius is still going to go from 0 to 1, and the angle is only going to go from 0 to pi halves. We could, of course, have the angle go from 0 to 2 pi, but since we're doing a quarter circle, why not? Our function is 1, and now dx dy becomes r dr d theta. What's wrong with what I've written? Yes? Yeah, dr is on the inside. So if I'm writing it like this, it's clear what's going on because I'm labeling, so I'm not going to make hopefully a mistake, but I should really switch these orders because I'm running r dr d theta. So I should really switch them and have theta goes from 0 to pi halves, and then r goes from 0 to 1. Okay. Which integral is easier to do, the r integral, the theta integral, or are they basically the same? Is either integral challenging? No. The r integral is I'm just finding the antiderivative of r, that's r squared over 1, 2. And the theta integrals are just the antiderivative of d theta, which is theta. What's nice is if you have an integrand that splits something in r times something in theta, and you're integrating over a rectangle, you can actually split the integral up into two one-dimensional integrals. So this is just 4 theta goes from 0 to pi halves of d theta, and then the integral r goes from 0 to 1 of r dr. Because when I do the r integration, whatever I get is a number that has no theta dependence. If I had instead, theta plus 1 to the r, that's going to be a terrible function to integrate. And when I integrate that with respect to r, there will be some theta that will be left over. I can split my integrand into an r piece and a theta piece. And since my region is rectangular, I can do the integrals one at a time. The theta integral is just going to be theta evaluated at pi halves and 0. And the r integral is just going to be r squared over 2 evaluated at 0 and 1. So we get 4 times pi halves times 1/2, which is pi. And that is the area of a circle of radius 1. If I wanted to do a circle of radius big R, this is the advantage of being at the blackboard. All I would have to change is now I go up to R. So this over here would just become a capital R. This would just become a capital R. This would just become a capital R, and we would just have a capital R squared. So it really wouldn't be that much harder to get a circle of radius big R. So I'm hoping that this is motivating the power of the change of variable formula. This was not a hard integral to do, or a hard pair of integrals to do. And we now have the area of a circle. Let's go one step further. What volume might you want to know? A sphere. Let's prove the volume of a sphere is 4/3 pi r cubed, given this change of variables. Now there are two ways you could do the sphere. You could do it as a 3-dimensional integral, or you could do it as a 2-dimensional integral. Imagine the equator of the Earth. And then just take that big circle, and then above each point, you go up until you hit the surface of the Earth. And that will give you your height. And you'll find the area under the top hemisphere. And that will give you half the volume of the sphere. So what would you then do to get the whole volume of the sphere? Multiply by 2. So I'm going to show you how we can very easily get the volume of the sphere. How many of you have ever seen a proof of the volume of the sphere? Greeks did this without calculus. Absolutely amazing, some of the calculations they did. That said, I know calculus and I'm quite happy to use it and avoid all of those geometrical stuff. In previous years, I've actually led trips to the Rare Books Library. If people want me to do that, let me know. We have first edition of Newton's Principia, as well as other artifacts like that. And you can see the huge difference in terms of how calculus was presented back then. Volume of a sphere. So since x squared plus y squared plus z squared is 1, we get z is plus or minus the square root of 1 minus x squared minus y squared. Let's do the more general case of a sphere of radius r. It's not that much harder, and this will save you doing the search and replace later. So what we want to do now is we'll integrate x goes from minus 1 to 1, integral y goes from minus the square root of 1 minus x squared to the square root of 1 minus x squared. My function, my height, is the square root of 1 minus, these should all be r squared, sorry. We're doing a circle of radius r. R squared minus x squared minus y squared dx dy, then we multiply by 2. And that is the volume of a sphere. And you can see the beauty of this. No, not beautiful, right? Opposite of beautiful. You now have to find an antiderivative of a square root. We're going to be evaluating that at square roots. You should be running with horror away from this. We do not want to do this integral. We want to switch to polar coordinates. What would this look like in polar coordinates? In polar coordinates, it would be 2, and now you would have theta goes from 0 to 2 pi, little r goes from 0 to big R, the square root of r squared. Now, what is x squared plus y squared in polar coordinates? In polar coordinates, x squared plus y squared is r squared. And then we have r dr d theta. So we have an r integration to do, we have a theta integration to do. Notice that the integrand just has r dependence. It has no theta dependence. We can split this up and do the theta, and we can do the r. This is going to be 2. Theta goes from 0 to 2 pi of d theta, and then little r goes from 0 to big R of the square root of big R squared minus little r squared r dr. Okay. The theta integration is not bad. What's this integral going to give us?
Theta.
It's going to give us theta, then we evaluated 2 pi and subtract 0, so we just get 2 pi. So we get 2 times 2 pi. Now we have to do this integration. This looks bad at first, but the integrand is the square root of r squared minus little r squared. In an ideal world, what would you love to have once you have a square root with an r squared inside? What would you love to have? To make this nice, to do a good use substitution. Negative. I can't hear you. Okay. What would you love, if you have the square root of r squared minus little r squared, and we're integrating with respect to little r, what would you love to have hitting this? We'd love to have a negative 2r. When you do your use substitution, I want to use almost like the chain rule. So if I let u equal r squared minus little r squared, du is going to be negative 2r dr. Do you see how this is going to be beautifully situated for use substitution? I like to do the following step. If r goes from 0 to 1, what does u go from? So when little r is 0, what is u equal to? Oh, so r is going from 0 to big R. So when little r is 0, u is equal to big R squared, and when little r is r squared, u is 0. So we have to be careful because of the minus sign. We want to make sure we don't forget these minus signs. We want to make sure we have the integration going correctly. So I'm going to write this really explicitly. It's going to be the integral r goes from 0 to big R, square root of r squared minus r squared, 2r dr with a negative sign. So I have to put a negative 1/2 over here. Right? And so now I'll get negative 2 pi integral u goes from big R squared to 0. And now I will get u to the 1/2 du. But if I switch the order of integration, that costs me a minus sign. So this is the same as 2 pi integral u goes from 0 to r squared of u to the 1/2 du. For a problem like this, you should be able to find minus sign errors. The volume of a sphere should not be negative. What function has derivative u to the 1/2? This would be 2 pi u to the 3/2 over 3/2 evaluated at 0 and r squared. Because now if I take the derivative of u to the 3/2, I'll get 3/2 u to the 1/2 divided by 3/2. Alright? The dividing by 3/2 gives me a 4/3 pi r squared to the 3/2 is r cubed. There's the volume of the sphere. That's not a bad result to get. And it all comes down from assuming that dx dy transforms to r dr d theta. This should really motivate us for the work that's coming ahead. Okay. Any questions about this problem? So most of this is doing just integration again. There's very little multivariable calculus. The multivariable calculus is in setting up the integration, or in justifying the coordinate change going from x and y to r and theta. And we'll show later why you get this extra factor of r when you do that interchange. But then you have a bunch of Calc 1 integrals to do. So you've got to remember your U substitution. You've got to remember your Calc 1 techniques. All right. So I want to end class by doing an example. It's going to be very similar to one in the book. So here's the parabola y equals x squared plus 4. And then I want to take the line and this would be the line y equals x plus 8. So down here, this is the point 0, 4. This is the point 0, 8. So this line intersects the parabola twice. It intersects it once over here and once over here. So my shape is going to look something like this. And I want to do an integration over the region between the parabola and the line. So the question is this region vertically simple? Is it horizontally simple? And if it's both, which one would you rather do? So first, is it vertically simple? Is there a lower boundary curve so that if I start at the lower curve and I move up, I only hit the surface once and only once? We all agree that this is vertically simple. I can start on the boundary, there's a lower curve, and there's an upper curve. It's vertically simple. Is it horizontally simple? If I start on the left and I walk, do I always hit only one point on the right? Yes. This region is also horizontally simple. This means you have a choice. How many of you have seen Ghostbusters? Right. Choose. If you make a bad choice, what should you do? Choose the other, right? So whenever you have a problem like this, start doing it one way. If it's not going well, pause. Put it off to the side and try the second choice. If that's not going well, go back to the first and maybe it's not as bad as you thought. Do you want to do this vertically or horizontally? Which one do you want to do first? Vertical. Why? So when we do it vertically, we have one curve for the bottom, which is always the parabola. So y1 of x is always going to be x squared plus 4. And y2 of x is always going to be x plus 4. If we do it horizontally, up until this magic point, we're integrating from the parabola to the parabola. And then from this point onward, we integrate from the line to the parabola. So it's a little bit cleaner to do it as vertical integration. We would need to find out where these intersection points are. So we would want x plus 8 to equal x squared plus 4. And that's how you would find the points of intersection. Well, this would be the same then as x squared minus x minus 4 equals 0, x equals 1 plus or minus the square root of 1 plus 4 all over 2. So x is 1 plus the square root of 5 over 2 and 1 minus the square root of 5 over 2. These are just me being a little bit cute. This is the golden mean. And so we would now have the coordinates of the 2 points. So we could say, let's integrate. X goes from 1 minus the square root of 5 over 2 to 1 plus the square root of 5 over 2. Y goes from x squared plus 4 to x plus 8, and then just our function f of x, y, dy, dx. And that would be how you would set up the integration for this problem. Okay. Any questions about this calculation? As a nice exercise, you should set it up horizontally with the split definition. My gut feeling is almost surely it's better to do this as a vertical problem. But sometimes, depending on what integrand you're given, it's better to do it one way than another. So for example, imagine I give you e to the xy, y. I can either do it dy dx, or I can give you e to the xy, y, dx dy. Would you rather integrate first with respect to x and then with respect to y, or first with respect to y and then with respect to x? Any thoughts as to which way would be better? With respect to x. Why would you want to integrate with respect to x first?
Because since there's no x, that's why
so the y is going to disappear. If I want to integrate this with respect to x, if I do a u substitution, I need to have a y dx because I have this presence of this y here. If I had e to the 7x, I would want to have a 7 dx. If I have e to the xy, I would want to have a y dx. If I try to do it this way first, oh lord, I'm now integrating with respect to y first, I would want to have an x. So I'd have to multiply by an x and then divide by an x. It's going to lead to a nightmare. So, all things being equal, I'd rather do the integration in this order first. And in a lot of problems, it's all going to come down to trying to figure out which is the best order. If it's a double integral, there's only 2 choices. Try one, if it's not going well, try the other.